Hello everyone, welcome back to my YouTube channel. Today we are going to learn an important and very interesting topic in data structures and algorithms called graph traversals. Here we will talk about breadth first search and depth first search. So let's get started. First I will explain about what is a graph traversal. Graph traversal means visiting all nodes. That means all vertices of a graph in a systematic way. First of all, I'll explain what is a vertex and what is an edge. This is an example for a simple graph. In this graph, all A, B, C, D, E and F are vertices of this graph, and any line that connects two vertices are known as an edge. Here the line that connects A and B is an example for an edge, and other lines that connects two edges of this graph are also examples for edges of this graph. Graph traversal is about deciding the order in which we visit these places. There are two main ways to do this: breadth first search and depth first search. First I will explain what is breadth first search. In breadth first search, it is a graph traversal method where we visit all the nearest nodes first and then move to the next level. It works level by level. Data structure used here is the queue, FIFO, which is also known as the first in first out. Now I will explain about depth first search. In depth first search, it is a graph traversal method where we go as deep as possible in one direction, then come back and explore other parts. It works like branch by branch. The data structure used here is stack or recursion. Here are the step-by-step rules for breadth first search. First, you must start from the given node, then visit the node and mark it as visited. Add all its unvisited neighbors to a queue. Remove the first node from the queue. Finally, repeat until the queue is empty. Now I'll tell you the step-by-step rules for depth first search. First, you must start from the given node, then visit the node and mark it as visited, then move to an unvisited neighbor, then repeat until no unvisited neighbor is left, and finally backtrack and explore other paths. Now I'll explain about breadth first search and depth first search by using three examples. Here's the first example I got, and using this graph I'll tell how breadth first search happens. First, you must visit any node in this graph. So I'll visit 1 as the first node, then I'll write 1 here. Then you must explore all the adjacent vertices of this visited node. The adjacent vertices of 1 are 2, 4 and 5. You must write those adjacent vertices in any order you like. So I'll write 2, 5 and 4 here. Now all these vertices are visited. Now using remaining vertices, the next vertex you must visit is 3. So you must write 3 here. Then you must explore all the adjacent vertices of 3. The adjacent vertices of 3 are 6 and 7, and then you must write those adjacent vertices after 3 here in any order you like. So this is the breadth first search using this graph. This is another example to explain how depth first search happens. In this graph, I'll visit any node first. So I'll visit 1 as the first node. So the next thing you must do is you must visit the next node after 1. Here it is 2, so you must write 2 here. In breadth first search, you visited all adjacent vertices of the visited node. In depth first search, it is not done. You must visit any node first. After that, you must visit the next node after that, and you can see that there are adjacent nodes here, so you must not visit them. You must visit the other node in this graph. The next node is 3, so here you can see that there are no adjacent vertices of 3 here, so you must write 3 here. So visiting nodes is done now. So as there are no adjacent nodes for 3 is there, you must visit the earlier node again. Here it is 2, and there are 2 adjacent nodes for 2. You must visit any node from here. I'll visit 6. You can see that there are no adjacent nodes for 6, so I'll write 6 here. Then come back to 2, then visit 7. You can see that there are no adjacent vertices here also, so I can write 7 here. I'll here now, and you must come again to 2. Then you must visit 1 again. You can see that there are 2 vertices that are adjacent to 1. They are 4 and 5. You must write any node from these adjacent nodes. I'll write 4 here. You can see that there are no adjacent nodes for 4, so you will go back to 1 and visit the other adjacent node of 1, so it is 5, so you must write 5 here. So you can see that all the vertices of this graph is written here. So this is the depth first search using this graph. Now I'll explain about breadth first search again using another example. Actually, this is a binary tree. Binary tree is also a graph. Using this graph, I'll explain how breadth first search is happen. The first level of this graph contains 1, the second level contains 2 and 3, and finally the last level contains 4, 5, 6 and 7. In breadth first search, you must write all these vertices in their level order. First you write 1, then 2 and 3, and finally you must write 4, 5, 6, 7 in their order. So I'll write 1 first, then I'll write 2 and 3, then I'll write 4, 5, 6 and 7. So in a binary tree graph, the breadth first search is done in level order. Now I'll explain about depth first search using this binary tree. Binary tree is also a graph. Using a binary tree, depth first search is done like this. First you must write 1, the first node of this graph. Then you must write 2. You can see that there are 2 child nodes for these 2, so you must write 4 here. You can see that after 4 nothing remaining, so you must go back to 2 and write the other vertex here. So I'll write 5. After 5 there's nothing remaining. You must go back to 2. Again you must go back to 1, and you must travel to 3. You must write 3 here. After 3 there are 2 child nodes, 6 and 7. You must travel to 6 and write 6 here. After 6 nothing remaining, so you must go back to 3 and travel to 7 and write 7 here. You can see that all the vertices are written here, and this is how depth first search is done using a binary tree. Actually, depth first search in a binary tree is a pre-order traversal. Now I'll explain about breadth first search using another example. This is the graph I used here, and I use a cube also. First you must do here is you must select the first you must select a node as the first vertex. So I'll select 1 as the first vertex, so I write 1 here, and also I write 1 here also. Then you must explore 1. The adjacent vertices of 1 are 4 and 2, so you must write 4 and 2 in this key, and also you must write 4 and 2 here. Then all the adjacent vertices of 1 are explored, and remove 1 from this key. Then the next node to be visited is 4, and you must start exploring 4. Here you can see that the adjacent vertex of 4 is 3, so you must write 3 here and also here. Then you can see that there are no more adjacent vertices for 4, and so you can remove 4 from this key also. Then you must visit 2. You can see that the adjacent vertices for 2 are 5, 7, 8 and 3. 3 is already entered to this cube, and so you must enter 5, 7 and 8 to this cube. 5, 7 and 8. You must enter these values to this red first search also. Now you can see that you explored all the adjacent vertices of 2, and you must remove 2 from this key. Then the next node you must visit is 3, and you must start exploring 3. You can see that the adjacent nodes for 3 are 9 and 10, so you must write 9 and 10 here and also here. There are no more adjacent vertices for 3, so you can remove 3 from this key. The next node you must visit is 5, so you must start exploring 5. The adjacent vertices for 5 are 2, 8, 7 and 6. You can see that we already visited those 2, 8 and 7, and the remaining vertex that I visit is 6, so I'll enter 6 here and I'll write 6 here also. And now you can see that we visited 1, 4, 2, 3, 5, 7, 9, 8, 9, 10 and 6, and they also contain in this breadth first search. So this is the breadth first search that can be performed using this graph. Now I'll explain about depth first search using another example. For this I'll use a stack also. The first thing you must done here is you must select a starting node as the first vertex. So I'll get 1 as the starting vertex, and you must explore 1. There are 2 adjacent vertices for 1, so I'll write only a 1 vertex here. After writing 4 here, I'll push 1 to this stack and start exploring 4. 3 is the adjacent vertex of 4, so I'll write 3 here, and after writing 3 I'll push 4 to this stack and start exploring 3. The adjacent vertices of 3 are 9, 10 and 2. I'll write a vertex here and push 3 to this stack, and you can see that there are no adjacent vertices for 9, so you must go back to 3 and go back to 3. So you must pop 3 here and start exploring 3 again. You can see that 10 is adjacent vertex of 3, so you must write 10 here, and there are no adjacent vertices for 10. After writing 10, you must push 3 again to this stack and start exploring 10. There are no adjacent vertices for 10, so you must go back to 3. So you must pop 3 from here and start exploring 3 again. The adjacent vertex of 3 is 2 here, and you must write 2 here and push 3 again to this, and then you must start exploring 2. The adjacent vertices for 2 are 5, 7 and 8. You must write only one vertex, so I'll write 8 here and push 2 to this stack and start exploring 8. The adjacent vertex of 8 are 5 and 7, so I write 7 here. After writing 7, I'll push 8 to this stack and start exploring 7. The adjacent vertex of 7 is 5, and I write 5 here. After writing 5, I push 7 to this stack. Then I'll start exploring 5. The adjacent vertex of 5 is 6, and I'll write 6 here. After writing 6, I'll push 5 to this stack and start exploring 6. You can see that there are no adjacent vertices for 6, so go back to 5. So I'll push pop 5 from this stack and start exploring 5 again. The adjacent vertex of 5 that is remaining here is 8, and it is already written. So I think that all the vertices of this graph are written in this breadth first search. This is the breadth first search using this graph, and this is the stack used here. Now I'll explain you about the application of breadth first search. Breadth first search is used to find the shortest path or exploring things level by level. Breadth first search always visits the closest node first. Because of this, breadth first search is perfect for finding the shortest path is an unweighted graph. As an example, finding the shortest route from your home to a shop, finding the minimum number of moves in a game. In GPS navigation and route planning, GPS system use breadth first search like logic to explore nearby roads first, then expand outward until the destination is found. Because we want a quickest or shortest route and not a long one, we use breadth first search. In social networks, users are nodes and friend relationships are edges. Breadth first search helps to find mutual friends and suggest friends of friends. As an example, if you search people you may know, breadth first search checks your friend list and then friends of your friends. Now I'll explain you about the application of depth first search. Depth first search is used when we want to go deep into one part before trying others. In cycle detection, depth first search helps detect cycles in graphs. As an example, checking if a road map has circular routes and detecting infinite loops in programs. Depth first search can track visited nodes and detect when a node is visited again. In path finding, depth first search is used to check whether a path exists between two nodes. For example, checking if there is a route from city A to city B and checking connectivity in networks. Depth first search explores deeply until the destination is found. In connectivity checking, depth first search helps find connected components in a graph. As an example, finding isolated networks, checking if all computers are connected is done. Thank you so much for watching this video. I hope this lesson helped you understand breadth first search and depth first search clearly. If you found it useful, please like, share and subscribe to the channel, and see you in the next video.